Okay, welcome to Algebraic Topology. In this class, we're going to be following Alan Hatcher's book pretty closely. It's online for free, and you can also purchase it for, I don't know, not too much on Amazon. I have a special relationship with this book. So, when I was your age, I did a study abroad experience in Oxford, and over the couple terms I was there, I went through this book with my tutor. It's the tutorial system. It was a very magical time of my life. And then I came back, and my last year at Stanford, I enrolled in a graduate level algebraic topology class where I went through the book again. So this book has really grown on me. It's a standard graduate introduction to algebraic topology. Advanced undergrads, accessible. It is a little bit technical at points in the reading. You have to work your way through, and you maybe won't understand every word as you're reading through the book, but I encourage you to spend some time wrestling through it, because I think you'll get a lot out of it. It's very well written, despite being a bit tense, and hopefully the lectures will help you quite a bit as well. Cool? Okay, I need to tell you about course logistics. I don't know what they are yet, so I'll figure that out next week or two and send you an email. This week, no homework or anything. By next week, I'll hopefully figure something out. It's 1 credit, so we won't take it too seriously. Okay. Today, we're introducing algebraic topology. And so I'll just say a few words about algebraic topology. And I probably should have prepared for this more, but maybe some of you can help me. Topology, Greek, yeah? Topos, meaning shape. So topos logia is the study of shape. So this is study of shape. And algebraic, algebra, Arabic, named after the inventor of algebra.
No, I think it's
Under variable or something, the word for variable, the word for unknown.
Or the way.
The way. Huh. Anyway, this isn't a linguistics class. Algebraic topology. So what is algebraic topology? The way we can think about it is within mathematics, you have different islands of knowledge. And over here, we have the algebra. Algebra, island of knowledge, where here you have things like group theory. And some of you have taken some abstract algebra before. You would have learned tools about groups, rings, all of this. You learn about that in algebra land. Over here, we have the island of topology. And topology is interested in the study of shapes and surfaces loosely. It's like geometry, but a little bit under the influence. And so you're a little bit loose in how we handle things. What algebraic topology is it's a bridge between these two lands. It takes some shape or surface, something that's kind of hard to grasp, something that's kind of loose, and transports it to the land of algebra, assigns it some algebraic structure. Now in the land of algebra, we can work with the structure. We can do nice, clean mathematics, and the base, whatever we discover in the land of algebra, is giving us some insight to this topological structure. So you can think algebra is the way we get a handle on the topology. So that's the big idea of algebraic topology. So today I would like to begin by introducing us to just some basic shapes, some basic notation we'll be using throughout the course. And the first object I'll introduce us to are a disk. So here's my notation. When I write D2, I just mean the two-dimensional disk. And so you might think of this as something like the set of all points x, y in R2 such that the distance from the origin is less than or equal to 1, say. Such that the square root of x squared plus y squared is less than or equal to 1. Well, we don't need the square root because the square root of 1 is just 1. So x squared plus y squared should be less than or equal to 1. This is how you can think about a disk. But this definition is not so important because for us, we're not going to really have this strict, there's no metric that we're dealing with here. So we don't need a definition like this. This is a disk. Sometimes I'll draw my disk like this instead. These are all disk, right? Okay. Idea is D2 is just two-dimensional. How about D1? Can you give me any guesses of what D1 should be? Just a line. So you might think it's the points of length up to 1 in the R1, but just think of it as a line segment, right? And sometimes I'll stretch and bend my line segments, I don't care. This is D1, these are all D1. How about D3?
Ball.
Yeah, a ball, a solid ball, right? And you might deform it to be a slightly different shape, but anything equivalent to this. I'll make more sense of what we mean by equivalent in the next lecture. And so forth for higher dimensions, right? You can go all the way up to dn, or n is whatever dimension you like. We can also go lower, d0, help me out. What should d0 be? Just a point. Just a point. Those are disk. We also have spheres. S2 is, I should draw down here. S2 is the two-dimensional sphere, but the two-dimensional sphere you think of as living typically in three-dimensional space. You can live in higher spaces too, but you typically think of it as three-dimensional space. So this is just the boundary of the ball. Likewise, S1 is the one-dimensional sphere, which we often refer to as the circle, right? So S2 is the boundary of D3. This is my notation for boundary. Is there an A in boundary? It's like half the alphabet in that word. The boundary of D3 is S2. The boundary of B2 is S1. So you help me out now. What should S0 be? Well, if we think of S0 as being the boundary of the one-dimensional disk, which is just the unit interval, or just an interval, what would S0 be? 2 points. S0 is 2 points. And in general, the boundary of the n-dimensional disk is the n-1 dimensional sphere. Happy? Okay. There are other surfaces. Here's a classic one. You might take a square and glue together the right side with the left side. I'm going to label this A and A just to indicate I'm gluing this side to this side. What do you get? Yes, we get, this is my way of representing the cylinder. If instead I glue the left to the right, but with opposite, flipping the orientation of one of them, what do we get now? Yeah, this is the classic, take a strip, glue together the sides, that's the cylinder, but now we're not going to glue them together the same direction, we're going to flip one over and glue them together, and we get this one-sided shape called the Mobius band. So it ends up looking, a little twist gets added. And we get the Mobius band. Mobius band or Mobius strip. Here's one more. Take a rectangle, glue the left to the right, glue the top to the bottom. This is going to be a glue the left to the right. Now I want to glue the top to the bottom. What's going to happen if I glue the top to the bottom? We get the surface itself, the torus, not a solid torus, just the surface of the torus. So when I say torus, I'm just referring to the surface. It's not filled in, it's just the surface itself. You can think that this A here got glued to this A, and when they got glued together, they ended up forming something like this circle. It's a circle because you also glue the top to the bottom, making it a circle. And here, this B gets glued to this B, which then gives you a circle going around the other direction. Okay, one last one. We're going to do the same thing, but I'm going to flip one of the directions. So A with A, B with B, but I flip one of the orientations. What am I going to get now? Yeah, so the way you can think about it is if you glue that B with B, you get a cylinder. So now I have a nice long cylinder if I'm gluing that B to B. I want to attach the A to the A, but I can't attach it around this side because it's the opposite orientation, so I have to attach it by bringing it in. So what you get is you get some cylinder. But then this part needs to attach back down to the base, not by coming around, but by coming inside and attaching to the base. And so you end up with my attempt at drawing a Klein bottle. Which you can see right here, the Klein bottle. Okay, are we happy with this way of drawing things? Okay. Well, let's try and step it up a level. What if instead of drawing a torus, I want to give gluing instructions to draw a torus that has two holes in it. So this is my two-hole torus, genus 2. If you've heard that word genus before. This is my two-hole torus. What set of gluing instructions will give me a two-hole torus? So the way we can think about this is I'm going to cut this two-hole torus in half. Let's first figure out how to just glue this right-hand side. This right-hand side is a torus that someone took a bite out of, right? So the right-hand side is just a torus that somebody took a bite out of. What set of gluing instructions would give us this? Well, this yellow piece should be left over. So this yellow piece is going to be glued to other things. It's going to be left over. And see if you can convince yourself it's exactly the diagram for the torus, except, so let me start drawing the diagram for the torus. So you have your A, and then you have your B. Okay, we can draw it this way. I'm going to draw it slightly different. And then we have A, and then we have B. If I had completed this, if I had just drawn A, B, A, B, that's just a torus, right? That's just a torus. What I'm going to do is before I complete it, A, B, I'm going to stick this line in. What happens to that line in the end? Well, the bottom of A gets identified with the bottom of A when you glue these together. So now it's at the top of B. So it's identified with the top of B. So it's identified with the top of A. So it's identified with the bottom of B. So it's identified with the bottom of B. This will get glued to itself. This will become a circle. And the rest of this folds into a torus. So this is the gluing instructions for the left-hand side. Then similarly, we can think of the right-hand side as just being another copy of a torus. So another copy of this. But since I've already used A and B, I'm just now going to use C and D. Notice the pattern, 2 in the same direction and 2 in the opposite direction. 2 in the same direction, 2 in the opposite direction to get the torus. That makes sure when you glue these C's together and glue the D's, you get the hole on this side. So now we know how to build the left and the right-hand side of the two-hole torus. How do we end up with the two-hole torus? Well, we just glue together this piece with this piece. So we just glue together this piece with this piece. And when you glue them together, what we're going to end up with is an 8-sided shape. So the two-hole torus you can get from gluing together this 8-sided shape that goes A, B, A, B, C, D, C, D. That's a two-hole torus. So now I'm going to test to see if you understand the idea. You tell me, what are the gluing instructions for a 3-hole torus? What can we glue together to get a 3-hole torus? For 2 holes, you need a stop sign. What do you need for a 3-hole torus?
Can you take a cross section that separates 1 hole from 2 holes? Then you can take our diagram for the 2-hole torus and have like an extra.
Yeah, so you can be like this. If you cut this guy off, you'd have a 2-hole torus with a line on the side. So there's like an extra line on the side right here. And then you just add in a torus to it. So you're sticking in 4 more sides. So what are you going to end up with?
12-sided shape.
12-sided shape. That's right. So let's try and sketch a 12-sided shape. So 12 is, we can first do the 4. And then we'll break these up into 2 each. And now we can read it off as A, B, A, B, C, D, C, D, E, F, E, F. This gives you the 3-hole torus. We can actually see a little bit more what's going on here. If we look like at what this A piece is, well, it depends how you fold it, but let's say A, let's say all these points, I mean, these points are all the same point, like this point gets identified with this point, now it's at the head of B, so it's identified with this point, now it's at the head of A, so it's identified with this point, but it's also at the back of D, so the back of D gets glued to the back of D, now it's at the head of C, so it's glued to the head of C, now it's at the head of D, so it's glued to the head of D, now it's at the back of C, so all those points are the same. All these, there's just one vertex here. It's all the same vertex. Let's just put that vertex like right there, right? I'm gonna forget about this yellow line now, so we glued it together, got rid of that. Then you can think of this A is just like some loop that goes around that part of the torus. So some loop. And the B is another loop where the B is like tracing out this direction. And your C, where would C be? Yeah, just around the other side. And if you change the order of these, that's fine, you know. The point is, your D, okay, I'm out of colors, let's just do white, be something like this. So you need 2 loops to describe a hole. Just like your original torus was described by 2 loops. And so when you have 3 holes, you're going to need 6 loops. But since you're gluing 2 together, you need 12 sides. And in general, a G-hole torus where we want to have G holes is going to need how many sides? You need 2 loops for each of the G, so you need 2 G loops, but then each loop is represented by 2 sides, so 2 times 2G, it's going to be a 4G sided shape. Where you have your 2G loops. Okay. So we can keep building up things like this, but what I want to do is describe a general way of building such spaces. And what I'm going to describe now is how we build what we call a cell complex. We're going to see all these things are examples of cell complexes, a cell complex. Sometimes you'll also see this referred to as a CW complex. Well, CW is not a reference to the failed media company. It's a reference to, so C is closure finiteness, W is weak topology. We may get into this a little bit. Don't worry about what that means for now. But let's talk about how we build a cell complex. So the way you build a cell complex is you begin with what I'm going to call the 0 skeleton, which is denoted x0. And what the 0 skeleton is it's just some collection of point or points. So maybe several points. Over here, in the example of the torus, my skeleton would be just a single point. So if I'm thinking about the torus, I have a single point. Let me up here build the torus one step at a time. So my 0 skeleton for the torus is just a single point. Then my 1 skeleton is what's going to happen when I take that point and I add to it some lines. So I'm going to add copies of D1 or lines. Possibly 1, possibly several. In the case of the torus, you only need to add 2 lines. So your x1 is your dot with 2 lines added. One which I'll draw like this, and one which I'll draw like this. I added 2 lines. But notice those lines were attached to the 0 skeleton. And so for each D1, there's some attaching map that explains how D1 gets attached to the 0 skeleton. In particular, it explains how the endpoints get attached. So it's a map from the boundary of D1, which is S0, that's the boundary of D1. This is the boundary of your D1, onto your 0 skeleton. And here, this is a really trivial map. Your phi is just the map that takes both endpoints and sends both of those endpoints onto your point in the 0 skeleton, right? And same thing for the red one. So this is a really trivial map here. But you might have, say if you start with 2 points, you could also have lines that connect those 2 points, right? It could be more interesting. What we're going to do next is we're going to move up to the 2 skeleton, which I'll denote by x2. And what I'm going to do now is I'm going to add some copies of D2, some 2-dimensional disk. So these are now my 2-dimensional disk. My 2-dimensional disk. According to some map, that's going to take the boundary of each disk. So the boundary of a disk is a circle, it's S1, and attach it to my 1 skeleton. And I claim that's exactly what this is doing here. This is a copy of your map. Because what it's saying is you glue the circle by beginning to glue it onto A, then onto B, then onto A, then onto B, respecting these directions. So if I give these guys some directions, the way it takes a circle, and you can imagine beginning to glue the circle first along this A, and now that's glued along this A, you're going to glue it along B. In this picture, it's going against the arrow, so we're gluing it now here. So what it does, it starts gluing a circle along here, then it glues it along here, and then it glues it against A, going against the flow, so going this way along A, and then glues it back along B. And so you should take like a minute to convince yourself that this is indeed how you build a torus. Right, this right here just is the 2 skeleton for a torus. You take that circle, you begin gluing it onto A, glue it onto B, glue it onto A, glue it onto B. And you might want to build like a wire mesh of this and imagine gluing on the, how you would have to glue on each one of these, the 4 sides of it. But that's really what this here is. This is a map describing how you glue the disk onto your 1 skeleton. Okay, and you could continue this. If you want to go higher, if you have a higher dimensional object you're trying to build, in general, you could have some n skeleton, xn, which is just adding some copies of dn via maps that are attaching each boundary of dn, so each Sn minus 1 to the n minus 1 skeleton. And you can keep doing this. Okay, so this is a CW complex, or a cell complex. Here I showed you one way to build the torus, but there are other ways you could have built the torus too. You didn't have to use 1 point and 2 lines to build your torus. What's another way you might have built your torus? So here I have 1 point and 2 lines. So I'll just record some data here. I've built my torus here so that if I count the number of D0s, there's 1 of them. If I count the number of lines, there's 2 of them. And then I count the number of disks needed, there was 1. Give me another way to build a torus. Let's use more points. Okay, so I'll give away the final shape. But let's use more points. Let's use, say, 4 points. Try and put this on the opposite side. Try and put this on the opposite side. Then what I could do is I could attach these 2 points above the torus. Attach these 2 points above the torus. Attach him going around. Attach him going around. I'll also attach him going around like this. And I'll attach him going around. And I'll attach those 2 points at the bottom as well. Okay, do you see this wire mesh I'm trying to build? So let's keep track of how many points we used. 4 points. The 0 skeleton is 4 points. For the 1 skeleton, how many lines did I add? 1, 2, 3, 4, 5, 6, 7, 8. Yeah? And now's the moment of truth. Can you tell me how many disks it takes to glue this together? How many disks I glue on to finish this guy up? Four? Yeah, that's right. So maybe this wasn't the optimal diagram, but I can try and draw it again here, and maybe this will make it a little bit clearer. So what we had done is we built this wire mesh, right? This is the 1 skeleton, it's your wire mesh. And now how do you glue on your disk? Well, one disk you glue here, and along in there. That's 1 on top of the front. And then you have 1 on the bottom of the front. And then 1 on top in the back, and 1 on bottom in the back. So you end up with a total of 4 disks. Okay. Either way, you can build a torus. So now you tell me, those who've seen anything related to topology before, what can we do with these numbers? What does this remind you of? The Euler characteristic. So the Euler characteristic, you've probably seen defined as something like the Euler characteristic. So you may have seen this in graph theory for planar graphs, or you may have seen this with polyhedron, right? Where you had some formula like the Euler characteristic, denoted by the Greek letter chi for characteristics, is often calculated as something like faces, number of faces, minus the number of edges, plus the number of vertices. Yeah? Well, now, using this language, it's just the number of two-dimensional disk minus, in your 2 skeleton, minus your number of one-dimensional disk, plus the number of zero-dimensional disk. But this is only if I have a 2-dimensional cell complex. I could be n-dimensional. In that case, you just continue the alternating sum. Or in general, you put a plus in front of all the even-dimensional ones. So it's the number of even-dimensional disk minus the number of odd-dimensional disk. So now you can define for arbitrarily many dimensions. And the nice thing with the Euler characteristic is that independent of however you chose to construct your object, the Euler characteristic's the same. If I take the alternating sum of this, I get 0. Or if I take the alternating sum of this guy above, I get 0. The Euler characteristic of the torus is 0. By way of contrast, someone tell me, what is the Euler characteristic of the sphere, the 2-sphere? So I'm asking for the Euler characteristic, I'll just write it here, of S2. Why is it 2? You're right. Can we see it here? Why is it 2? Well, how do you build S2? There's a couple ways you could build S2. Here's the easiest way to build S2. You just take a single point, that's your 0 skeleton, no lines for your 1 skeleton, and then a single disk for your 2 skeleton. And then the map to attach the disk to your 0 skeleton, which is also your 1 skeleton because you're nadding to 1 skeleton, is just the map that takes everything on the boundary of the disk and glues everything onto that point. What do you do if you glue the whole boundary to that point? It's like you've bunched up all the edges together to a single point, and you end up with a picture like, well, I'll put the point down here. You end up with your disk, some picture like this. These aren't lines, I'm just trying to show you it has some three-dimensionality, right? So you get your sphere. So it has 1 D2 and 1 D0. So when you add it up, it'd be 1 for D2, 1 for D0, and nothing in the middle. So it ends up being just 1 plus 1 for your Euler characteristic. But there's other ways you can build S2. Another way to build S2 is lots of ways. I don't know, let's take a point, and let's stick a line around it. Now I have my equator. Now how many disks do I need to attach to it? 2. 1 on the top, so I'll glue 1 disk along the top to my equator, and I'll glue a second disk. Here's my second disk. I'm going to glue, this is me trying to give it some shading, glue a second disk to the bottom. And now the number of 0-dimensional points is 1. The number of 1-dimensional disk is, lines in this case, is 1, so it's minus 1, plus the number of disks. I added 2 disks for the 2 hemispheres. Still comes out to be 2. Or if you started with 2 points, you now have 2 lines and 2 hemispheres. You know, however you build it, the Euler characteristic stays the same. Okay. I think we'll gain a pretty good grasp for how we build up spaces from disk. Let's look at a more complicated space. Let's try to understand real projective space. So we began with RP1, let's say. RP1. So do you know the definition of RP1? This is the set of lines through the origin of R2. In general, RPN is just your set of lines through the origin of Rn plus 1. Okay, so let's try to understand this a little bit. So I have R2, but each line in R2 corresponds to a point of RP1. Kind of weird. This is a point, and then very close by is this other point, and then this other point, and so forth. These are each points. So there's another way you can think about this. Another way to think about RP2 is you could say, okay, well, each of these lines, you could think of by where it hits the unit circle. And then you can say it's points on the unit circle, except this point and its antipodal point, its point on the opposite side, both represent the same line, so therefore it represents the same point. So it's points on the unit circle where you make the opposite points, antipodal points, identified. So I could say this is S1 identifying antipodal points. Antipodal, which means opposite. Opposite pole, antipodal. But if all the points on bottom identified with the point on top, now this is redundant. So we might as well just think about this as the top half, the top hemisphere, where this point on the right is identified with this point on the left. All these points on top identify something on bottom, so we can just collapse them all. Now we just have the top arc, top half of the circle. But we need to remember that this point on the right is going to be glued to this point on the left. Maybe I'll just put like an A next to both of them, so remember these get glued together. What is that? Yeah. It's just S1. S1 antipodal points identified is itself just S1. So RP1 is just S1. Okay. How about RP0? Now instead of lines passing through R2, it's going to be lines passing through R1. So lines passing through R1, well, there's just one of those lines, right? So it's just one line, so this itself is just a point, right? A single copy of D0, it's just a point. How about RP2? Well, now when you think about lines passing through R3, right? So we have all these different lines passing through R3. But instead of thinking about the whole line, we'll just think about where the lines hit the unit sphere. And each line will hit the unit sphere in two locations, antipodal points. So we need to glue together antipodal points of the unit sphere, right? But if we're gluing together antipodal points of the unit sphere, then we can just think of the bottom sphere as being glued to the top, so we really only need to keep track of the top hemisphere. Except, along the boundary, you still have antipodal points being identified, right? So the boundary is a circle with opposite points identified. What is that? Well, we just talked about that. A circle with opposite points identified is S1. So the boundary itself is S1. But what I want to point out is that this boundary is S1, but that means it's also RP1. So let's notice what we had to do. RP0 was just a point. RP1 was a line glued to that point. So to move from RP0 to RP1, we just added a copy of a line. We just added a D1. To move from RP1 to RP2, we had a disk that was glued to, the boundary of it was RP1. So we just took a disk, D2, and glued it onto RP1. And if you keep thinking about how you build it up each step, I want to argue at each step, you're just adding a copy of a higher dimensional disk to the previous RPN. So that in general, RPN is defined recursively as just RPN minus 1, where you glued onto it a disk of dimension, let me make sure I get it right, dn. Which means RPN will have one copy of D0, one copy of D1, one copy of D2, all the way up to one copy of Dn. So what's the Euler characteristic of RPN? What's the Euler characteristic of RPN? Yeah, it depends if it's even or odd. So in the even cases, you think, like you start counting, even is positive. So this gives you a +1, right? And then this guy gives you a -1, and then +1, and -1, and so forth. If n is even, so in the case where n is even, it's going to come out to be, if n is even, it'll be +1, that's right. And if n is odd, it'll be 0. It's like, that'll be 0, that'll be 0, and so forth. Okay, cool. So maybe this was not obvious from just the definition, but we're getting a powerful technique to begin thinking about spaces, helping us visualize them. Okay, what I want to do for today, for the rest of today's class, is I want to talk about how to combine spaces to get new spaces. Not just build up cell complexes, but operations to combine cell complexes. Ooh. So let's talk about some operations on spaces, operations on these cell complexes. I'm going to go through several operations. The first one I'll go through is just a product. If you have two spaces, x and y, I want to talk about what I mean by x cross y. And I think the best way to do this is just with a few examples. So let's say I have the space S1, and I want to cross it with D1. Okay, what I mean by D1 is just a line. So sometimes for D1, I'll just write it as 0, 1, the line. If you prefer -1 and 1, that's fine. We often use 0, 1 for convenience. Sometimes I'll write I, meaning interval, right? Okay, so you can instead think of this as S1 cross the interval I. But to be explicit, I'm just going to write 0, 1. What do you think this means? What's like a good interpretation of this? Well, you can think each point at S1 is going to become an interval. Well, that is, you have S1, each point becomes an interval. Each point becoming an interval. Each of these points has become an interval. What is this that I get? Just a cylinder. So this just gives you the cylinder. Or if I had instead drawn it like this, an annulus, right? So cylinder or an annulus. Again, there's no metric here, so don't worry that this length is a little bit less than this. There's no metric in this class. Right? A little bit too, a little bit too loose-minded for metrics here. Okay, here's another one. S1 cross S1. A circle full of circles. What is that? Yeah, you can think you take a circle, and at each point, it becomes a circle. Each point is, I can't draw it for all the points. There's infinitely many. I'm trying to draw enough to give you a good idea of what's going on. What is this going to become? Yeah, this is just a torus. It's just a circle full of circles is just a torus. Okay? How about D2 cross S1? What is D2? Yeah, it's S1 filled in. D2 cross S1. Each of these points becomes a circle. Each of these points becomes a circle. Each of these points become a circle. Each of these points become a circle. It becomes a solid torus. It becomes a solid torus. We happy with cross product? I'm sorry, the product? the product of two spaces. One or two more things I'll mention. dm cross dn. Okay, like let's think of some examples. What is d0 cross d3? Well, d0 is a point, and d3 is the solid ball. What happens when you cross something by a point? Well, each point stays a point, right? So crossing by d0 doesn't do anything. d0 is like the identity operation. So in general, we could say d0 cross any space just leaves that space. You're just crossing by a point. So that's just d3. Okay, what if I want to do something like d1 cross d2? d1 is interval, line segment. d2 is the disk. What do I get when I cross those together? They're like, oh, some kind of like thickened wedge thing, right? But it's filled in, it's solid. What is that? That's just a d3. Okay, typically you draw d3s like this, but it's a d3 that got smashed a little bit, right? That's d3. Anyone want to make a conjecture about what dm cross dn is? dm plus n, that's right. I'm just adding the dimensions. How about, here's one more interesting one. What if we include a couple crosses? What if we do a product of, say, this one's a little bit tricky. S1 cross S1 cross S1. The product of S1 with S1 with S1. This might be a little bit hard to think about. Well, we know these first two give us a torus. Not a solid torus, just the surface. And now we want to cross that the torus with S1. Now this might be hard to think about. So it may help if you first think about what is S1 cross with just an interval, say 0, 1. Right? What would that cross 0, 1 do? What was that word? Yeah, it would thicken it up. You would have your shell, and this cross 0, 1 thickens the whole thing, right? So you might think it ends up being like a torus with like a drilled out center, right? It's like has this drilled out center. You have the overall torus, but this center has been drilled out inside of it. Hopefully we can see what's going on here. Okay, so it's like someone came in. It's like a jelly donut where someone ate all the jelly, right? It's a jellyless donut. All this jelly's been eaten out. It's hollow inside. There's no jelly in there. No jelly. What a sad world we live in, right? Okay. But now that you have that picture in your mind, what is S1? This S1 is exactly 0, 1, identifying together the 0 and the 1. Gluing together the 0 and 1, right? If you just glue together the 0 with the 1, you get S1. So the way to think about this is you're in this jellyless donut, but as you travel through and you get to this edge right here, it's identified with that point on the inside. Each of these lines is like this line where one end gets identified with the other. You're like in this jellyless donut, but when you get to this point, you're back at this point. So there's no boundary to this shape. Whereas here there is boundary. I should take a second and talk about boundary. If I want to calculate the boundary of a product, this is my notation for boundary. The way we do it is it comes out to just be the boundary of x cross y union x cross the boundary of y. So let me give some examples of that. What's the boundary of D2 cross the interval? So this is D2 cross 0, 1. So we can visualize D2 cross 0, 1. D2 cross 0, 1 is just the solid torus, a solid cylinder, right? So what's the boundary of that? Well, let's use the formula. It's the boundary of D2 cross 0, 1 union D2 cross the boundary of 0, 1. Let's talk about this first piece. What is the boundary of D2? S1. S1 cross 0, 1. That's this first piece right here. S1 cross 0, 1. That's just going to look like S1 cross 0, 1. That's just a cylinder. Yeah. Union, what's the boundary of the interval 0, 1? 2 points, right? It's D2 cross 2 points, the point 0 and the point 1, which just means 2 copies of D2. Each point of D2 becomes 2 points, becomes 2 copies. So this guy down here is saying 2 copies of D2. A copy of D2 and a copy of D2. And when you glue those together, what does it give you? Well, just the boundary of the cylinder, right? Okay, also need to keep track of how they're glued together. Won't worry about that too much. But here's another way to think about this. This is just D1. What is D2 cross D1? This is just D3. I'm just asking you, what is the boundary of D3? What is the boundary of D3? It's just S2. And sure enough, when you glue this together, it's just S2. Right, so it all agrees. Coming back to this example, well, what is the boundary of S1? What's the boundary of a circle? There is no boundary. It's empty. The boundary of S1 is empty. So when I take the boundary of this whole thing and start taking the boundary of each piece, it all becomes empty. So this has no boundary. This has no boundary. Because when you're inside, you never get to the boundary. You travel to the end, you're back inside. Whereas this guy does have a boundary. The boundary of this guy is, well, when you do the boundary of S1, it becomes empty, so that piece is nothing. When you do the boundary of S1, it becomes empty, so that piece is nothing. But when you do the boundary of the interval, you get 2 points. So it's S1 cross the points 0, 1. What is this saying? What is the boundary of this guy? Just 2 copies of the torus. The inside torus and the outside torus. So here you have an inside torus and an outside torus. But when it becomes S1, those get glued together. And now there is no boundary. Okay, let me show you one more thing you can see with boundary. This is pretty neat. What is S3? How can we think about S3? So this might seem kind of weird. Like, what do I mean by S3? Well, it's the boundary of the 4-dimensional ball. We're not used to thinking about 4-dimensional balls, but you can. The 4-dimensional ball is just the product of a 2-dimensional ball and a 2-dimensional ball, which is just, using our boundary formula, the boundary of D2 cross D2, union D2 cross the boundary of D2. The boundary of D2 is S1. So this is S1 cross D2 union D2 cross S1. What is S1 cross D2? Yeah, S1 cross D2 is, okay, let's try and draw this in a consistent way. I'll draw my S1 going around this direction. So that means my D2 is coming around here. It's the solid torus. Solid torus. So here we have my solid, trying to draw here a solid torus. Solid torus. This is also a solid torus. But this being opposite suggests the way you should think about this S1 is moving, the circle moving the other direction. So you should think about this guy more like, here's my D2, and my S1 moves around like this. So it's also a solid torus. It's another solid torus. This is saying if you glue together two solid tori, you get S3. This is really counterintuitive. And so I encourage you to take some time to think about this. But the way to begin thinking about it is take the center of this, like this circle right there, and glue this bit in. So like stick that in the middle, right? And then as you start coming up here, that's like gluing along all this bit. And as you're coming down, all this down here is getting glued to the bottom part. But what's going to happen is like, it's not just, if it's a cylinder, you can kind of glue it and kind of try and stretch it, right? But what happens is like this bit here gets stretched and it fills in all the space outside. Because it's like, it has to connect back upon itself. So maybe first you break it open, you try to glue it, but then you have to glue this on itself and ends up filling all the space, and it becomes what we call a one-point compactification of R4. So essentially what's going on here is just like how you can think about a disk as being, just like how you can think of like a sphere, S2 as corresponding to R2 through like this classic projection you've probably seen before, where points down here correspond to points on here, but then on the very top there's a point at infinity. The same thing is going on in S3, is you have each point being filled up in S3, but then there's a point over here that corresponds to like a point at infinity. When you try and stretch this over, it hits all the points off at infinity. And so when you're trying to glue this bit on at the end, you're going off to infinity. So this is kind of mind-boggling, but you can think about that. Okay, I've only told you about products, and there's a whole lot more operations I want to tell you about. And I don't know if we have much time. Let me just mention one or two of them, and then we'll pick up with more as we need them. Maybe the only other one I'll tell you for now, just because it's so significant, is quotients. So we know how to do products. How do we do quotients? Okay. So a quotient, what do I mean by division? What do I mean by something like D1 divided by S0? Well, D1 is just the line. And what is S0? 2 points. So here I'm thinking, what is the S0 that naturally lives inside of D1? Well, it's these opposite points. And so when you quotient out, what you're left with, in general, x quotiented by y is going to be the space x minus y with the space y identified to a point. Identified to a point. So these 2 points I'm going to identify to a single point. And what I end up with? Those 2 points glued together to a single point. This is just a copy of S1, right? Okay, more examples. If I want to do something like, if I want to do something like D2, quotient out by S1, my D2 is this disk. This S1 lives on the boundary. If I take all those points on the boundary and glue them together to a single point, what do I get? S2. We're getting the hang of this? What if I want to do something like S2 quotient out by S1? Well, you always have to ask, like, which S1 are you talking about in S2? But a lot of times, it's pretty obvious what's in mind. And here it doesn't really matter which one you pick. It ends up looking the same. Here's my S2, right? And even in drawing S2, to make it three-dimensional, I'm forced to draw that S1, aren't I? So there's my S1 inside of S2. Here's my S1. What happens if you grab that S1, you shrink it all to a single point? What do you end up with? What is it? Yeah, it's two S2s, but they're like stuck together at a point, right? It's like you have this point here, and you have an S2 on top. It's like you put a belt and you made it really tight until it gets shrunk down to a single point. Okay, we have a name for this. When you have two spaces stuck together at a point, we just call that the wedge. This is S2 wedge S2, where wedge is just sticking them together at a single point. Okay, I'll do one last example. What I want to do is I want to take a sphere, and I'm going to attach a line joining the point on top to the point on bottom. Let's call this arc, attaching the point on top to the point on bottom, let's call that arc A. And let's call this arc, attaching the point on top to the point on bottom, let's call that arc B. And I'll call the overall space X. Let's think about two things. First of all, can you tell me what is X quotiented by A? And then can you tell me what is X quotiented by B? So we're just practicing building up our intuition here. Okay, what's going to happen if I quotient by A? That means I'm shrinking A to a single point. So what does that end up looking like? Like one of these pastries? Have you seen these pastries before? But it's got connected itself. There's the point where A got shrunk down to. And this guy is your sphere. So it's a sphere where your north pole comes down and touches the south pole. That's X quotiented out by A. How about X quotiented by B? What is that going to look like? Yeah, I see all these hand motions going on, right? You have your sphere, but you can think like this north and south pole came down, got pulled down until they're all identified. And so you have a circle connected. And using my language of wedge, what would I call this space? S2 wedge S1. So this is a wedge here. So there's another operation I slipped in. Okay, so we've talked about a few operations now, and hopefully this has given us a good grasp of spaces. These are the tools we're working with. This is the topology side of algebraic topology. Where we need to start moving is how can we take these spaces and translate it into the language of algebra? And that's what we'll be doing in this course as we continue our study of algebraic topology.